The purpose of this presentation is to provide the viewer with a basic understanding of fabric filtration methods used to control air pollution and control devices under this category. We will cover what are fabric filters, what is fabric filtration, the three common types of fabric filters and their design and components, proper operating conditions which include the modes of the cleaning operation, and the filter methods and material composition. Causes of decreased performance. Performance monitoring. In filtration processes, particles are removed from the contaminated gas stream by depositing them on filter material. The filter is usually in the form of cylindrical fabric bags, hence the names fabric filter or bag house, but it may be in the form of cartridges that are constructed of fabric, sintered metal, or porous ceramic. In general, fabric filters are capable of collection efficiencies greater than 99%. One way of distinguishing between different types of fabric filter collectors is the method used to clean the filter material. As dust builds up on the filter surface, the pressure drop across the filter increases. In order to avoid excessively high pressure drops, the filter material is cleaned periodically. The most common methods of cleaning are shaking, reverse air, and reverse pulse or pulse jet. These cleaning methods are the three most common designs of fabric filtration systems. Another way of distinguishing between different types of fabric filter collectors is based on the way they operate. The three modes of operation are intermittent, periodic, and continuous. Intermittent collectors are used on processes that operate intermittently. When the process shuts down, the collector goes through a cleaning cycle and then shuts down and waits for the next processing cycle before starting up. Most intermittent collectors clean by shaking, but could also clean by reverse pulse. Periodic collectors are used on processes that operate continuously. The total fabric is divided between several modules or compartments. This allows a compartment to be taken offline and cleaned, while the remaining compartments stay online to provide filtration. Most periodic collectors clean by shaking or reverse air, but could also clean by reverse pulse. Continuous collectors are also used on processes that operate continuously, but they do not have compartments that shut down for cleaning. Instead, individual rows of bags in the collector are cleaned, while the remaining bags continue to provide filtration. Continuous collectors usually clean by reverse pulse, but could also clean by reverse air. As the name implies, shaker collectors clean the bags by gently shaking them. The shaker collector has a tube sheet between the vertical casing and the hopper. The open bottoms of cylindrical bags are attached to holes in the tube sheet, and the closed tops of the bags are attached to the shaking mechanism in the top of the casing. The contaminated gas stream enters the hopper, flows through the holes in the tube sheet, and into the inside of the vertical bags. Since the bags are closed at the top, the gas stream flows through the bags, leaving a dust cake on the inside. Periodically, the gas flow through the collector or compartment is stopped, and the bags are shaken to clean them. The dislodged dust cake falls into the hopper and is removed from the collector. The reverse air collector is very similar to the shaker collector. The collector has a tube sheet between the casing and the hopper. The bottoms of the bags are attached to holes in the tube sheet. However, the closed tops of the bags are attached to a support structure in the top of the casing that holds the bags under tension. The contaminated gas stream enters the hopper, flows into and through the bags, again leaving the dust cake on the inside. When it comes time to clean the bags, the gas flow through the compartment is stopped, and another gas flow is introduced that flows in the reverse direction. This gas flow is usually taken from the cleaned gas stream being discharged from the operating compartments. To keep the bags from fully collapsing during the reverse airflow, rigid rings are sewn into the bags at intervals along their length. The dust cake dislodged by the reverse airflow falls into the hopper and is removed from the collector. The gas that was used for cleaning flows out of the hopper and into the hoppers of the operating compartments. The fabric used in shaker and reverse air collectors is usually a lightweight woven fiber material. The fiber that is used is chosen based on the abrasive characteristics of the particles, the chemical characteristics of the particles in the gas stream, and the temperature of the gas stream. The openings in the fabric weave are about 20 to 60 micrometers. The collector's ability to remove small micrometer and submicrometer particles is due to the accumulated dust cake and not the fabric itself. The fabric is usually cleaned about once an hour to remove some of the dust cake. However, intermittent collectors may be designed to operate longer between cleanings. Reverse pulse or pulse jet collectors clean the bags using short duration pulses of compressed air. The collector has a tube sheet that is located near the top of the vertical casing, and the bags hang from the holes in the tube sheet. The contaminated gas stream enters through the side or hopper of the collector and flows into the bags and up through the tube sheet, leaving the dust cake on the outside of the bags. A wire mesh cage is located inside the bags to keep them from collapsing. Cleaning is accomplished by directing the compressed air pulse to one or a few rows of bags, while the other bags continue to provide filtration. The collector is usually not shut down or isolated from flow while cleaning. The dust cake dislodged by the compressed air pulse falls into the hopper and is removed from the collector. The cleaning system consists of a compressor, an aftercooler, a dryer, an oil trap, a storage manifold, solenoid and diaphragm valves, and laterals or blow tubes. The compressor generates relatively oil-free compressed air that is delivered to the storage manifold at about 60 to 90 psig. The aftercooler cools the compressed air as it comes from the compressor. The dryer removes moisture, and the oil trap removes any oil that might be present. The solenoid and diaphragm valves sequentially deliver the compressed air from the storage manifold to the lateral pipes or blow tubes that are located just above the tops of each row of bags. The laterals have small holes in them that direct the compressed air into the center of each bag. The fabric used in pulse jet collectors is usually a heavyweight felted fiber material. The fiber that is used is again chosen based on the characteristics of the particles and the gas stream, and on its ability to withstand the forces of cleaning. As with woven fabrics, the collector's ability to remove small micrometer and submicrometer particles is due to the accumulated dust cake and not the fabric itself. The fabric is usually pulsed several times an hour to remove some of the dust cake, but may be pulsed much less frequently when the dust concentration is low. Cartridge collectors are similar to pulse jet collectors. The unique feature is the design of the filter element. Essentially, all cartridges are shorter than pulse jet bags. Some have simple cylindrical designs, while others have a large number of pleats or other complex shapes in order to increase the filtering area. The filter media is usually a felted fiber material, but may be constructed of sintered metal or porous ceramic. Another type of collector that utilizes filtration to remove liquid and solid particles from a gas stream is the high-velocity air filter, or HVAF. This type of air control device is also known as high-efficiency air filtration, or as a HEAF unit. HVAFs collect particulate matter by impacting the particles on a linear filter mat that is slowly unrolled and banded around a porous rotating drum, or travels over a flat bed. The contaminated gas stream passes through the rotating drum or flatbed, leaving the particle cake on the outside surface of the mat. These units may have a mist eliminator on the outlet gas stream to capture droplets escaping the filter mat. As the pressure drop across the filter increases, the mat is advanced to expose fresh media to the gas stream. The spent filter mat is disposed of after one use. Another single-use particle collector is the high-efficiency particulate air filter, or HEPA filter. HEPA filters are used for the high-efficiency removal of submicron particulate matter from a gas stream that has a low contaminant concentration. The filtering media is a continuous sheet of fiberglass or cellulose paper that is wrapped in an S pattern across corrugated metal or ceramic support strips. The filter unit, which ranges from 3 to 12 inches in depth, is mounted in a gasketed retaining frame to prevent leakage around the filter media. The contaminated gas stream passes through the filter media, leaving the dust cake on the upstream surface. HEPA filters are typically changed when the pressure drop across the filter increases by 2 inches of water. However, HEPA filter systems may be designed to operate with pressure drop increases of up to 10 inches of water. To review, the common types of fabric filters classified by cleaning method are shakers, reverse air, and pulse jet. The common types of fabric filters classified by the mode of operation are intermittent, periodic, and continuous. Other component and design considerations for fabric filters include the gas flow rate, the filter material and surface area, the cleaning system, and the particulate matter characteristics of the contaminated gas. Most problems that affect the performance of a fabric filter collector are associated with the conditions the fabric is exposed to and with the cleaning frequency and intensity. Some of these problems include high temperature damage, condensation of acid vapor, blinding caused by moisture, oil, or condensed organic material, blinding caused by ineffective cleaning, excessive cleaning frequency or intensity, abrasion by particles, abrasion by rubbing against other bags or the casing. The ability to evaluate potential problems during a field inspection will depend on how well the system is instrumented. Most large fabric filter systems are well instrumented. However, smaller systems may have limited instrumentation. Performance evaluation of these systems will be difficult unless measurements of important parameters are made. There should be two goals in any field inspection. First is to evaluate the source's compliance with any rule-specific monitoring requirements and with the provisions of the Title V permit. In addition, parameters that influence performance should be evaluated to see if there are shifts from their baseline values that could indicate reduced collection efficiency. The most direct indicator of the performance of a fabric filter is the opacity of the discharged gas stream. An increase in average opacity from the baseline value provides an early indication of developing problems. If there is an opacity monitor, past trends in opacity should be evaluated. Before doing so, the adequacy of the data should be evaluated by inspecting the condition and integrity of the measurement system and checking the calibration frequencies and procedures and the maintenance records for the instrument. The timing, duration, and severity of opacity spikes should also be evaluated. A decrease in opacity when a specific compartment is offline usually indicates a failed bag in that compartment. If opacity spikes occur consistently as each compartment is brought online after cleaning, overcleaning of the bags may be a problem. For pulse jet collectors, an opacity spike that occurs when a specific row is cleaned usually indicates holes in one or more of the bags in that row. An average opacity that is consistently above the baseline value may indicate a leaking bypass damper. Another instrument that is useful in evaluating fabric filter performance is the bag break detector. Although these instruments provide an indication of emissions, they do not satisfy requirements for opacity monitoring. However, they are quite sensitive to concentration changes and can provide an early warning of increased emissions. The inlet and outlet temperature of the collector should be checked. The inlet temperature should be compared to the temperature limit for the fabric being used. Frequent exposure to high temperatures can damage the fabric and cause holes to develop. Low inlet temperatures could result in acid, moisture, or organic vapor condensation. Acid condensation will weaken the fabric material, causing holes to form. Moisture or organic vapor condensation can cause portions of the fabric to blind. When a portion of the fabric is blinded, the remaining fabric will operate with a higher airflow than intended, which can cause particles to seep through the fabric. An increase in the temperature difference across the collector indicates increased air infiltration. Acid, moisture, or organic vapor condensation problems can develop in portions of the collector if the cooling is excessive. Another important inspection parameter is the pressure drop across the collector and across individual compartments. Pressure drops across the collector that are higher than baseline values can be caused by undercleaning, fabric blinding, or by the blockage of bag inlets by overflowing hoppers in shaker and reverse air collectors. Lower pressure drops across the collector may indicate overcleaning. Shaker compartment pressure drops that are not zero during cleaning and reverse air compartment pressure drops that do not change sign during cleaning indicate a failure of the dampers to isolate the compartment. Changes in the cleaning system parameters can affect performance, and these should be checked. Increases in the frequency or duration of cleaning can result in overcleaning and in excessive bag wear, while decreases in frequency or duration can result in undercleaning and increased pressure drop. These parameters can be evaluated from timers in the control panel. For pulse jet collectors, the pressure in the compressed air manifold should be compared to the baseline value. Higher compressed air pressure can result in overcleaning and excessive bag wear, while lower pressures can result in undercleaning and increased pressure drop. The actuation of the diaphragm valves should also be evaluated to be sure all rows are being cleaned. This is done by simply listening for a regular pulse rhythm. There should also be a sharp sound to each pulse, indicating that the valves are working properly. If possible, the clean side conditions in the collector should be evaluated. This should only be done on a collector that is not operating or on a compartment that is isolated from the system. If they are willing to do so, ask plant personnel to open the collector for you and conduct your evaluation by looking in from the outside. Do not enter the collector under any circumstances. In shaker and reverse air collectors, look for the accumulation of excessive quantities of fresh dust. This can result from holes in the bags, holes in the tube sheet, and leaks where the bags attach to the tube sheet. Visually check the bag tension. Shaker bags should be slightly loose, while reverse air bags should be under tension. Look for bags that bulge at the bottom. This is an indication of hopper overflow. In pulse jet collectors, also look for the accumulation of excessive quantities of fresh dust that are indicative of leaks. Check that the laterals are properly aligned across each row of bags and that the holes are located so that the compressed air enters the center of the bags. Misaligned laterals can cause the compressed air to be directed against the side of the bag, eventually causing a hole to form. Visually examine the interior of the bags for indications of moisture or oil in the compressed air. Excessive air infiltration, bag blinding, and undercleaning may result in decreased gas flow rate from the source. Fugitive emissions and decreased hood static pressures are also indicators of these problems. To review, in determining if a fabric filter system is working efficiently, field personnel should observe, if possible, any visible emissions, opacity monitoring data, bag break detector indication, inlet and outlet temperature, air infiltration, pressure drop, and what cleaning problems pressure drop changes indicate, frequency and duration of cleaning, clean side conditions in the collector, which include excessive quantities of fresh dust, bag tension and other bag conditions, and pulse jet laterals alignment. indications of decreased gas flow rate. The inspector should always be aware of the air pollution sources need to be in compliance with applicable rules, and to observe the source's records and the control device's physical condition. Fabric filter systems have many safety considerations, including confined space hazards, hot surfaces. Field personnel should never enter the inside of a fabric filter device. This type of equipment has legally specified methods for confined space entry under OSHA Rule 29 CFR 1910.146. Further training and experience will be necessary to complete all field tasks safely.